Hello friends, this is a MATLAB demonstration of the concepts that we learned in lecture 3.6, in particular the concept of periodogram. So, I am going to show you how to compute periodogram starting from scratch, that is starting from FFT, although there exists a routine called periodogram in MATLAB that does for you. What I will do is I will show you how to do this by yourself, and then you can compare the results of this with what periodogram gives you. I will briefly talk about what periodogram gives you, but I will not really walk through the routine and the use of that routine in this session. So, this is an addendum to lecture 3.6. So, first what I would like to go over is the set of commands that are associated with generating the signals of interest. So, we are going to generate 4 different signals. The first 2 are deterministic signals, the remaining 2 are noisy versions of the first deterministic signal that I am generating here, all right. In fact, the noisy version is slightly different, it contains 2 periodicities. So, sorry about that. So, let us look at these 2 deterministic signals. What I have is the first signal is going to be generated at a frequency of 0.2, and so is a second signal as well. The only difference between these 2 deterministic signals is the length. I have 100 samples of in the first case and 107 samples in the second case. There is a reason why I have chosen these numbers. So, these are fairly straightforward commands to generate a sine wave of this particular frequency, 0.2 cycles per sample. So, this 0.2 refers to the discrete time frequency of the signal. As I said, in both cases the frequency is 0.2. Now, let us look at these 2 signals which are the noisy signals that I am generating. At first I generate the noise free signal which contains 2 frequencies of 0.1 cycles per sample and 0.25 cycles per sample. Again, there is a reason why I have chosen these 2 frequencies, and they are going to be I am going to generate 100 samples of this mixed sine wave, and I generate 2 noisy versions of the deterministic signal. In the first case I am going to add mild amounts of noise, in the second case I am going to add large amounts of noise. Now, the purpose of working with these 2 signals is to see how, if I apply the concept of periodogram to noisy versions, what result comes out when I do that, because we have learned periodogram purely for deterministic signals. So, let us generate the signals. As you know, in MATLAB you can just divide your code into different modules. I am going to actually run this particular module itself or section itself, and I have done that, and let me take you to MATLAB here. It clearly shows if I ask the list of variables, it shows that it has generated x1, and let me clear everything for you and then rerun, so that things are very clear to you. So, I have generated. So, now I have these signals x1, x2, x3, which is the noise free version of the noisy signals, y1 and y2 are the noisy versions of x3. So, this fact is verified. Now, let us compute the Fourier transform or the DFT using the routine FFT and then compute the periodogram. So, FFT, as I said, is the routine that computes the DFT for you. You should look up the help on FFT to understand its syntax and the algorithm and so on. So, I have computed the FFT of x1 here. Now, here in the second line here, you should pay attention on line 18. In fact, what I am doing here is I am creating the set of frequency points as a result of computing this DFT via FFT. So, what I am doing is the first frequency point is 0 and the interval is 1 over n1. We have already seen that DFT computes with a frequency resolution of 1 over the length of the signal. The last frequency in my set is 0.5 minus 1 over n. Ideally, this should have been 1 minus 1 over n, but because of the conjugate symmetry of the DFT, I only need to walk up to the half and look at the power spectrum. The power spectrum is going to be symmetric for with respect to negative and positive frequencies. So, I am only walking up to the half, not exactly half, but 1 over n short of 0.5, and that is why I create the frequency vector this way. Then I compute the periodogram, that is fairly straightforward. I take the magnitude square of the DFT coefficients, divide by n1, and then I plot a stem plot. The stem plot is the correct one to do because the DFT is only computed at the grid points. The rest is all decoration of the plots, and prepare underscore figure is a routine that I have written to decorate it further, annotate it further, and so on. So, likewise for the second signal as well, it is the same story. So, let us generate these two plots and see what I get. So, this is the second plot that I have. Let us look at the first plot. Let us magnify this. Now, this is the periodogram of the first signal. Remember, the first signal has a frequency of 0.2, and I had generated 100 samples of that signal. The periodogram correctly detects the frequency component of the signal. It says exactly at 0.2 there is a peak, elsewhere the DFT is 0, or the periodogram power spectral density is 0, or you can say the power is 0. So, that clearly tells me that there is a single frequency component in x1 of frequency 0.2 cycles per sample. So, I have to be very clear with the units. What about the other signal x2, which is also of the same frequency, but I generated 107 samples of it. But now it says that apart from, in fact, the first thing that you should observe is that it does not even correctly detect the frequency which is 0.2. It actually shows that there are many frequencies, of course, within the vicinity of 0.2, but it does not hit 0.2, and this phenomenon that you see here is called spectral leakage. What has occurred here, keeping aside all the math, a simple way of understanding spectral leakage is, in the given data record, the signal of interest has not completed integer number of cycles, it has completed fractional cycles, and therefore, not only you do not hit the exact frequency, but the spectrum at the frequency 0.2 is actually it actually spreads around to neighboring frequencies, it leaks, and that is called the spectral leakage. So, this has occurred primarily because the data record does not contain a full or integer number of cycles of the sine wave. Of course, in practice what do? I do not know the frequency. So, how do I collect a record such that integer cycles are recorded? Then in fact, if I know the frequency, I do not even need to do a Fourier analysis. Well, in practice what happens is you will have to use some window functions, which I will talk about in the case of short time when we talk about short time Fourier transforms, which will mitigate the spectral leakage, it will not completely eliminate it. However, the good news is that if you collect large samples, then it does not matter really whether the signal has completed fractional cycles or integer cycles, because the number of full cycles will be so large that the fractional effect of the fractional cycle will be minimal. So, as n becomes larger and larger, and I leave that as an exercise to you, you can choose for example 1007 samples and see how the spectral periodogram looks like. You will see that the spectral leakage would come down. Okay. So, we will talk about spectral leakage more formally when we talk of windows in short time Fourier transform. Now, let us move on to the noisy versions of the signal. Again, the purpose is to show you how, when you apply the concept of periodogram to noisy signals, things change, whether do they change or not is what we will see. After this, I will take an ideal random signal where there is no sine wave and compute the periodogram and show you what it is. So, let us look at the periodogram of the first noisy signal. Despite the addition of noise, I am able to detect those two frequencies 0.1 and 0.25. Here there is no spectral leakage because both these frequency components have completed integer number of cycles in the length of the signal. That is the reason I have chosen these two frequencies. However, if you look at the periodogram of the second signal where we have added large amounts of noise, what we mean by large is the signal to noise ratio is 1 here, and you should verify why it is 1. Earlier the signal to noise ratio was 25. Now, still the periodogram is able to detect the frequencies quite vividly, but then there are other competing neighbors here which bring in a lot of ambiguity. You are not sure whether these peaks here are due to noise or due to the signal itself. So, that is the problem of having large amounts of noise. Of course, then there are algorithms which detect the levels of noise, and then you can filter the noise from this data and rerun the periodogram and so on. But the purpose of this example was to show you that you can still use the periodogram to detect the frequencies when the signal to noise ratios are fairly high. Ideally, you should not be using periodogram if the signal is purely noisy, and that is the last example that I am going to work for you here. So, let us generate here 1000 samples of a random signal, ideal random signal known as the white noise. It is mean 0, variance 1, and I am going to compute the Fourier transform of this white noise realization, 1000 length realization, and we will create here the corresponding frequency vector. So, what we are going to do here now is we are going to evaluate the periodogram of the signal over the first half as we did earlier, and then obtain a stem plot. In fact, because we have 1000 observations, it may be better to plot the regular plot itself. So, look at how it looks like. This is how the periodogram of a white noise looks like. Now, how do I know if this is correct or wrong? Well, theory says that the spectral density of a white noise process should be flat, that is, it should be a horizontal line running across frequencies, running over frequencies. But what we have here is a very erratic display of the spectrum. There is no way I can see straight away that there is the underlying theoretical one is a flat one. So, this is the problem of using periodogram on a purely noisy signal or a signal which has large amounts of noise. Of course, there are improvements to this method known as modified periodogram methods and so on for random signals, and we are not going to discuss this further. Just to give you a feel of when to use a periodogram and when to use modified versions of it. So, I would like to quickly go over the documentation on periodogram. I am not going to show you how to use it, but I leave that as an exercise to you. Verify the results that we have obtained manually, that is by manually computing the periodogram with the results that you get from the MATLAB routine. So, let us just quickly walk through the documentation on periodogram. In fact, I am not sure how well you can actually see here. So, let me actually go through the help in the screen here. Okay. So, what does the periodogram do? Let me take you to the start of the help here. It returns the power spectral density, but it uses the it returns the power spectral density in terms of angular frequency. So, that is the expression that you should be using. What we have calculated is power spectral density in terms of cyclic frequency. So, when you are comparing, please be careful, compare the right things, and there is an option called window which we have not discussed in detail, but I mentioned this, that windows can be used to mitigate the effects of spectral leakage. By default, there is no windowing that is performed if you do not specify the window. Now, there is something called here NFFT, which is the number of frequencies at which you are evaluating, and you should check what are the default values of the NFFT. Each routine uses a different number for this. We have used NFFT equals the number of observations itself, but periodogram may use something else. And finally, if you go down here, it can also return the power spectral density in terms of the cyclic frequency, but then you have to specify the sampling frequency and so on. What you could do is you could obtain the periodogram, the power spectral density in terms of angular frequency, simply multiplied by 2 pi. That will actually give you the periodogram in terms of cyclic frequency. And there is something called a one-sided spectral density, two-sided spectral density, and a centered one. Now, this is the last point that I want to mention. The power spectral density is symmetric with respect to frequencies. Therefore, many a times what is reported is a one-sided one. That is, what is done is the power spectral density on the negative frequencies is actually added to the positive one, except at the 0 frequency, and that is called a one-sided power spectral density. So that the area under one-sided power spectral density still turns out to be the total power. So, the area is preserved. Two-sided is nothing is done, that is the default power spectral density for both negative and positive frequencies are returned, and centered is where the PSD itself is returned as a vector where the center frequency is 0. So, if you look at the vector of PSDs that it returns, the center value corresponds to 0 frequency. So, these are the 3 different options. You should see what is the default option. I believe the default option is the one-sided power spectral density that periodogram returns. So, you have to be careful. We did not compute one-sided power spectral density. We computed two-sided power spectral density. So, if you want to compare the results that we obtain with what periodogram gives, then you should use NFFT equals number of observations. You should not window, and you should ask for a two-sided power spectral density, and you should multiply what you obtain with 2 pi. So, these are the 4 different things that you have to do to compare. Thank you.